All right, so today we're going to be talking about tilings and tessellations and the connections between them. And I want to start by directly showing that connection. So for an equilateral triangle's tiling, and I'll get into more of what's involved in that, what that's really saying is there are these triangle shapes and they are connected so that each triangle has three triangle neighbors. And that condition is enough to say, okay, there's going to be 6 of them that go around in a loop, and we're going to see the same style of connection everywhere. Then we can come over to the origami tessellation realm and say those connections between shapes, those are pleats. The shapes are twists. And this is a rare case where the finished tessellation actually looks like the tiling. And here I've put a dot in the center of each twist and drawn a line between twists that share a pleat. The pleat is going around that corner. And you can see the same exact pattern of each triangle has 3 triangle neighbors, and it takes 6 of them to get back to the original, as we saw in the tiling itself. So these twist tiles, this is an idea that's coming from Lang's twist tilings and tessellations. And I would show you more of the book, but my top-down camera is not connecting today for whatever reason. And the idea is developed really mathematically in Lang's book, where you're first learning about the flat foldability conditions of individual vertices, places where folds come together. And then you're learning about twists, and then you're learning about twist tiles, and then you're learning about repeating patterns and tilings and tessellations. And today I want to assume that if you're on my channel, you already know what a twist is, and you already know some of these properties of flat foldable twists, namely that they have pleats coming out of them, they have some shape in the middle, that shape is rotating and then laying down flat. And in my situation, I'm usually talking about twists that are folded on some background grid. So you don't need to laser score the paper or pinch particular folds. You can set up your pleats and then create the folds for the central shape in the twist as it's coming down flat. So that basically guarantees a flat result. You're not saying, I have this collection of folds, will it fold flat? You're saying, I have this collection of pleats, and I'm going to put them into a flat state, and the paper in the middle is going to do whatever it has to do to get to a flat state. And then you get a flat state. So I find that much more of a natural case for looking at twists. And when we are talking about twists, there's 2 ways to really look at them. There's this view where it's already folded flat, and then there's this view, and these are the 2 twists that we were looking at in that photo: a right-handed closed triangle twist and a left-handed closed triangle twist. And those handednesses are based on which way the mountain folds lay down over the valley folds. If that's aligning with how your left hand rotates versus how your right hand rotates. And there's all kinds of different triangle twists. Both right and left-handed, you can go as big as you want. And what's true for all of these twists, including twists on the opposite side of the paper is that they all have these same 3 pleats leaving them. It's just how those pleats meet each other in the middle that's determining the different sizes. So you've got these same 3 pleats. Each of these 3 pleats has the same distance, 1 grid spacing between mountain and valley folds. And therefore, each of these different twists has the same effect on the broader pattern, namely that it has 3 pleats leaving it. Those pleats have 1 grid spacing between them, and they're in these particular orientations relative to each other. So I can go ahead and short circuit that description by saying, okay, I'm going to draw on a triangle, and I'll make that nice and bold so y'all can see it easier. So I'm going to draw on this triangle, and each of my edges of the triangle has 1 pleat leaving the edge. Specifically, that pleat is leaving the edge perpendicularly. So then I could take that crease pattern, and if I'm folding on a piece of paper and I happen to have the open triangle form more easily visible, increase this so you can see. So the pleat is leaving the edge perpendicularly, therefore the edge is straight in the unfolded state, and it's still straight in the folded state. So we've got the same triangle with just twisty stuff happening in the middle, no matter how we look at it, whether it's folded or unfolded. And that is going to be true. I could do that for any of these sizes of triangle twist. And those 3 directions are going to be the same. In the case of these on the top row, that's going to be up and left, up and right, and straight down. On the bottom row, I have them flipped, but it's the same triangle shape. And what Lang emphasizes in his Twist, Tilings, and Tessellations book is that these triangles that are drawn around the twists are actual things that are embedded in the tessellation itself. My view is more abstract, that as long as your pleats are matching up, you don't need to actually embed the tiles in the tessellation itself. And that frees me up to do all kinds of things like hybrid twists, extended symmetries, different kinds of tilings. Like, for example, with this structure, you cannot, well, basically you only get 1 tessellation per tiling if you're making it embed exactly, because you would have to have only twists that that are on the same side, and then like that's a whole other problem if you're trying to like embed the tiles in the actual tessellation. So I could say, all right, I've got this triangle idea, and we saw that triangle idea playing out in the tiling. So now I can take any, and I'll get rid of that dark triangle, I can take any triangle on the top row and any triangle on the bottom row, because I do have to consider, I have to match right-handed things with left-handed things. And that's a property of the tiling called two-colorability. So if we take a look at the tiling for those triangles with the two colors, we can see that showing up very nicely. And then we can take that coloring and say, okay, let's say the red ones are right-handed, the white ones are left-handed. And we're going to say, okay, let's take a random example, this guy and this guy. Then we can come in and grab another template and paste it in. And I just noticed in the chat earlier you were asking about the complicated looking triangle in the middle. These guys, those are the cursed triangle twists, and I do have a video on cursed twists. So that's something that you can check out. I think in that video I did both the cursed square and the cursed triangle. So if you search cursed square, you'll also come up with a tutorial I did on only the cursed square. But again, even the cursed twists have that same property of they have the three pleats. They're all one spacing between mountain and valley folds. And it's those three different directions. So those would also fit in, excuse me, when we're picking two twists to alternate. And I'm going to stick these a little closer together just so we can get more repeats on the amount of grid that we have. And if you want to explore more about these triangle twist patterns specifically, I do have a video in the foundational structures series on alternating triangle twists and like best practices for folding those. So now these two triangles basically define my entire pattern. I can group those, duplicate, and start copying. And actually I think I didn't shorten the other two pleats here. So you want to make sure that all of your pleats are the same lengths. And then I can start copying out, and I can say this pattern is going to repeat forever. So I've got my loop of 6. I have my 2 triangles that are alternating, and that is a pattern that'll repeat forever. And I can say some crazier things about the equilateral triangles. I just want to show a visualization of this process that we just did. It's basically saying, okay, we're going to alternate twists in this pattern. I need to pick a twist A, and then I need to pick, is the next twist going to be on the same or the opposite side? And is that twist going to be, in this case, closed or open? What we just saw was twist A being double open. Excuse me. Grab some water. So this pattern that I just drew out isn't even on this decision tree. It's kind of off this branch of even more open. And then we chose a closed triangle twist on the back side. So this is a very incomplete list of what patterns can be made. We can see the one that we were looking at in the beginning folded on a different grid. And there's so much variability that we can get because we're ignoring the specific triangle on the tessellation itself. Like with that specific triangle, we could get this closed triangles tight with the closed triangles on the same side. We could get this open triangle corners with open triangles on the same side, but we'd be missing out on these other 4 patterns that use closed and open triangle twists, either on the same or alternating sides. And we'd also definitely be missing out on all of these variations on these patterns where we have different spacing around different twists. So there's a lot more that we can find out about tessellations that can be folded on particular tilings than can be found just by drawing twists in the tiling itself. So the equilateral triangles is kind of a simple case of tilings. There's a lot more that we can do with it. And we can also use this to analyze more complex structures. So, for example, this guy in here is, in the crease pattern, a closed hexagon twist with open triangle twists around it, but those open triangle twists have one edge that is a valley fold instead of mountain fold. But what's coming out of this whole area is 6 pleats. In this case, they happen to be double depth pleats. And they are leading into triangles. So functionally, what's going on there is that I have a hexagons and triangles tiling. So I have hexagons surrounded by 6 triangles, and each of those triangles is surrounded by 3 hexagons. If I remember which keyboard shortcut is Zoom, there we go. There we see more of this structure. And if we wanted to take a look at the skeleton for that structure, we can see that it does indeed match. What's kind of crazy about this is that we can take that example of hexagons and triangles and pull it into a really different form by saying, well, we don't actually need the next hexagon to be the same as the first one. We can take that and say, well, as long as I have 6 pleats in those 6 directions, it's still a hexagon, and I can put whatever hexagon I want in that next overlap. So instead of these 2 pleats from triangles overlapping to form a copy of this twist in the center, I can pick a different twist. And that still works, and it still leads to 6 triangles, 3 of them close and 3 of them far, on the pleats from this hexagon. Now I've changed where my symmetry positions are in the tiling. So instead of having my my tiling with, and here we go with the coloring. So instead of having my tiling with this coloring, where every hexagon is the same, every triangle is the same, I'm using this coloring, where the central hexagon is one twist. All the triangles are the same triangle twist. But this other hexagon is a different choice of hexagon. And it's in a position of threefold rotational symmetry, where things on three sides are the same. So this layer of symmetry and the layer of tiling are closely related. Like, you can't pick a symmetry that doesn't comply with the tiling, but they're not identical. So that definition that Lang had of a tiling is something that you draw your twists inside of doesn't actually hold mathematically when you start thinking of the tiling as more of a guarantee that the pattern can fold flat. So what do I mean by a guarantee that the pattern can fold flat? Well, when you have these twist tiles, like we were looking at with the triangle twists, I'll bring back our triangle here. What this is saying is that the contraction in the paper from this plate, well, I'll match with the mouse from this plate, plus the contraction in the paper from this plate, plus the contraction in the paper from this plate, those all balance each other. And overall, and we can see this in this twist that I have in a tile here, those three directions balance each other. And if I had more paper here, it would be flat. So not taking into account the bumps from the extra layers on those pleats. These three directions of pleats with these sizes balance. And that's an equivalent statement to saying this triangle is a closed shape. So the triangle is a closed shape. If we come down to the rhombus twists, those rhombi are closed shapes. We have the four different directions where we have the same distance between the mountain and the valley fold. They're in specific angles. So this one and this one, there's 120 degrees between them. This one and this one, there's 60 degrees between them. And we see the twofold rotational symmetry. So holding it this way is the same as holding it this way. So that fact that these lengths and directions create a balanced polygon, that is a big part of the twist tile. And so taking that information back into the tiling, I can say this hexagon is a shape that goes around and connects. And therefore it's balanced in and of itself. And then it's going to a triangle, which is a shape that goes around and connects and is balanced in and of itself. And we have these shapes connecting, and there's no gaps. There's no edges that are not connected to something else. I'm saying with respect to assuming that this pattern keeps repeating forever. Because clearly in this drawing, there are edges that are not connected to things, but they keep repeating like the rest of the pattern. And there's a whole other topic of like, what are the different ways that this could repeat? And I'm going to cover a lot of that in Tessellation Academy this year. But the fact that these shapes fit together without gaps and each shape on its own closes up is what guarantees that my pattern that is based on those shapes and that connectivity will be flat. So assuming I use twists that can fold flat, like interactions of pleats that match with these shapes that fold flat on the inside, then I can say the pleats themselves, as they run out into other things, will lay flat. And like I can draw a circle around it, it will lay flat. And that draw a circle around it idea is coming from another book, Ben Parker's 6 Simple Twists, his circle cutout idea, which is really, really similar to this idea of the polygon that has the proportional pleats connects in the end. That's the same idea as Ben's circle cutout theory. And we can take that combination of things. Okay, we've got these shapes that are all closed. They're all connected to each other. There's no gaps. That is what guarantees that my pattern will fold flat. And furthermore, on the tiling, I see how things repeat. And I can apply different symmetries to that, but I still see how it's going to repeat, how many different choices I have. In this coloring of the hexagons and triangles tiling, I have 2 choices. What's in the hexagon? What's in the triangle? And technically a third choice of how far apart are those 2. If I have the other coloring that I showed before, I have 3 choices. What's in the hexagon? The dark hexagon. What's in the triangle? There's only one triangle. What's in one color of triangle, shall we say? What's in the light blue hexagon? And in order to really use this symmetry, the thing in the light blue hexagon has to be different from what's in the dark blue, because otherwise it just degenerates to the coloring we had before. And here also there's just one choice of spacing. What is the spacing between the dark hexagon and the triangle? And that's going to determine, because I have pleats overlapping that tell me where the light blue hexagon has to be once I have the dark blue hexagon and the triangles around it. So that's the design side of, we can use these tilings to create new patterns. And when we're doing that, we see in the tiling both a guarantee that the pattern will repeat and will fold flat, and how many choices we have as we're folding. The other thing that we get from these tilings is a suggestion, more or less, of how to fold them. So this is the key thing when you're first starting out with folding origami tessellations. You want to know, how do you fold any particular tessellation? And so you can go in and say, well, I want to have a hexagons and triangles pattern. And I'm going to start in the center. Let's say I have my grid on a hexagonal sheet of paper. I start with the hexagon in the center, and then I add on the next layer. And that layer has 2 triangles for each hexagon. And you could, and you'll see in a lot of my Advent of Test tutorials where we're only going this far, that I'll teach to fold the inner triangles and then the next hexagons and then the outer triangles. But as you go into more and more repeats, what's going to be easier is, for example, if we already have this inner bit, to say, okay, I'm going to add these two triangles and this hexagon. And with the inner bit, that's going to create a smooth outline. At that point, I'm not going to have any pleat overlaps. So if my pleats are always leaving the tile boundaries perpendicularly, if I have 1, 2, 3, 4, 5 tile boundaries in a line in the same orientation, then I'm going to have 1, 2, 3, 4, 5 pleats leaving that tile boundary all in the same direction. So that's what's really powerful about these tilings, is it constrains the directions of the pleats even when it does not constrain the exact placement of the center of the twist. And so as you go further and further out, I didn't finish the story with this guy. So we would add 2 triangles in the next hexagon, and then we would work our way either up to this edge or down to this edge, depending on how the pattern is interacting with the grid, and say, okay, I'm going to add 2 more triangles and a hexagon, 2 more triangles and a hexagon. And at that point, I again have this smooth boundary, and then go to the next edge, add up to here, next edge, add up to here, next edge, add up to here, and then complete the final edge. And that can be applied all the way out further and further and further as you go through these patterns. So that's a style of folding that I call rings around the center. There are 2 other styles of folding. One of them is extremely similar to rings around the center, and that is, there are rings, but there are going to be twists that are cut in half by the edge of the ring. So here I have a hexagon, rhombus, triangle, rhombus tiling. And in the next ring around the center, I can add in 6 more rhombi, but I can only add half of the next hexagons for each of the 6. And that's specifically 3 pleats coming from these 3 rhombus twists. And then I have either a half hexagon tube. If it's a closed hexagon, I have some complicated arrangement of pleats if it's an open hexagon, or I could literally set it up as a trapezoid twist and just try not to squash it to avoid having an extra crease across the middle. And then I keep going out, and these triangle gaps, by the way, if you see a triangle gap like that, it's going to be filled with a triangle interaction of pleats. And then there will be a pleat headed off this way, even though in the final twist there will be pleats headed off in the rhombus directions instead of just the one direction like the triangle. So this is where you would have a triangle wrap or a 3-way intersection of mountain folds. And you can keep going out and seeing, okay, these are the things that I get to finish this round. These are the things that are incomplete. And by the way, this rhombus shape is filling in for part of a hexagon. That would be where you would have a compound wrap, because it's a corner that would be filled in with those pleats that are 60 degrees apart. So there's a lot going on with these tilings that is more than meets the eye. There's the design side of things, there's the folding side of things. This idea of the pseudo tiling breaks. I do, by the way, have videos on these 3 different styles of folding repeats of patterns. These pseudo tiling breaks have really opened up like a lot of patterns that were really hard for me to fold before. And there's a lot more tilings, I feel comfortable saying, that do not have the edges of tiles forming a straight line that passes all the way through that we saw in the hexagons and triangles tiling. And that means that there's a lot of patterns that need this technique in order to be folded more easily. One final technique for folding patterns is in stripes. So these stripes, they may not be clear. Well, first I'll show one where the stripe is not strictly necessary, and then I'll get into some where it is more necessary to fold in stripes. So in this pattern, small squares and right triangles, it's one that we've talked about in Tessellation Academy before. We have 3 directions of tiling breaks. All the vertical lines go straight through, all the horizontal lines go straight through, all of the diagonal lines go straight through. So it would be a decent candidate for folding rings around the center. We could definitely do that. But the way that these patterns are set up is in these stripes for the most part. Because that is where you see the symmetry of the pattern. So there's 4 positions of 2-fold rotational symmetry in this tiling. 2 of them are in the square twists, and 2 are between the square and triangle twists. And then there could also be mirror symmetry between stripes. But what's going on with these is you want to start with 1 square, and then you're adding on the right triangles needed to get the next squares in the stripe. And then you're extending that stripe to the ends of the paper, and then adding stripes, probably 1 on one side and then 1 on the other side. But I put together these files to do an animation, and so I did want to, finish at some point. And so this style of folding is particularly suited to the way that this pattern repeats, but it's not 100% necessary to fold this particular tiling in stripes. Let's take a look at another one, hexagons and triangles 2-fold. And I'm going to put this up here, and when you look at the crease pattern, you might be tempted to say, oh, I see what the stripe is. The stripe is these connected hexagons. But if you look at that, those connected hexagons have a very bumpy outline. And that means that there's constantly going to be pleats crossing each other if you put in the full stripe of hexagons first. So what we can do instead is start with 1 hexagon, and then, like the stripe that I just showed with the squares and right triangles, we can add the triangles needed to put in the next hexagon above and below. Then we can extend that stripe further and further and further until we reach the edge of the paper. Typically, these patterns are folded on triangle grids on squares or rectangles. So there is going to be an edge of the paper. You're going to want to hit that edge unless you have some alternative way of dealing with all of the pleat overlaps that would result if you had that very bumpy line as the end of your folding progress. And then you can add a stripe on one side, a stripe on the other side, and that would be working from one end or the other, and do the hexagon, the 2 triangles, the hexagon, 2 triangles, hexagon, 2 triangles. And that'll probably be, once you have the first triangle set up, it would be the triangles on opposite sides of the hexagon. So you're not getting this bumpy corner. You want to keep that as smooth as possible. And then more stripes and more stripes and more stripes as you work your way out to the other edges of the paper. And here you could choose to stop at whatever end of a stripe you want, because you do have that straight line all the way through where all the pleats that cross it are parallel. So those are the 3 folding styles that I work with and that I see as possible when you're working in a tiling mindset for folding your origami tessellations. There is one more thing that I wanted to go through today, which is some examples of patterns that use another tiling, and kind of explaining some things that often come up as questions when I talk about tilings with my students. So here I have the hexagon double rhombus triangle tiling, and when you look at it in the 2-color form, it might look kind of confusing, but still there's only one hexagon, there's one white triangle, or white rhombus rather, one red rhombus, one red triangle. I do have this smoother, shall we say, colored form, which shows, okay, yeah, this rhombus is actually distinct from that rhombus, and we have that other triangle. So we have these 1, 2, 3, 4 different twist positions. And then we can go in and say, well, what's my skeleton? How does that shape up? And one of the things that I hadn't shown yet is times when the skeleton doesn't necessarily look like it's not an exact copy as you go between the crease pattern and the tiling. So I want to bring up a pattern called Holly, which is the pattern on the cover image for this live stream. And we're going to take a look at what the crease pattern is, how that matches with this tiling, and how we can see, let's see, can I get it to do just the one side? Maybe not until I have this one just on. Well, it's being difficult. Oh well. Okay, buddy. We're going to just put that right there, and then this guy, I'll pull out the layers as needed. Okay. So, whoops, not that one. This guy. So we've got this crease pattern for Holly, and what I want to emphasize is that the tiling does not strictly overlay on the crease pattern. So I've got them in roughly similar size factors, But you'll notice that, for example, the orientation between repeats of the hexagons in this crease pattern is not the same orientation. So this orientation here is not the same as this orientation here, and that is perfectly fine. We're not trying to overlay these different patterns. What we can see is there's a hexagon twist, there's this closed rhombus on the front, there's this open rhombus on the back, and there's this closed triangle on the front, or sorry, on the back. And those are the only 4 twists that we have in this pattern. We can see that the open rhombus is acting as a position of 2-fold rotational symmetry. We see the same thing on opposite sides of it. The triangle is acting as a position of 3-fold rotational symmetry. We see the same thing on 3 different sides of it. And of course, the hexagon is a position of 6-fold rotational symmetry. So those characteristics match what we see in the tiling. The hexagon's a position of 6-fold rotational symmetry, the triangle's a position of 3-fold rotational symmetry, the rhombus is a position of 2-fold rotational symmetry, and then there's that other rhombus. And to really double check that this is the same connectivity between the two, we can pull up the skeleton, which snaps in once you scroll, and see, okay, we've got this kind of kite flowery thing going on around the hexagon. Got that same kite flowery thing around these hexagons. And those kite flowery things are touching tip to tip. Check. That is indeed touching tip to tip. And we have this little bumpy kind of triangle-ish shape with the triangle in the center. Same bumpy triangle-ish shape. Excellent. So those are indeed the same connectivity. And the other thing that I often hear is like, why is the tessellation not looking like the tiling? And here we have the folded form of this particular pattern. Let's see, that one will do a half full. So here in this folded form, we don't see discrete boxes for each shape. In fact, they're remarkably overlapping. The hexagon kind of has its own discrete area, but then this rhombus is really overlapping with the rhombi on either side and also with that triangle. So we're not gonna see these discrete boxes like we would think about from the Twist, Tilings, and Tessellations book. And I think that the tessellations that come from that are more interesting than if we did have everything strictly separated out. And also, there's a decent chance that this tiling, if you did try to do it as discrete boxes, would not work, like at all, because the rhombus twists, the mountain fold of the rhombus twists don't all go straight to the center of the rhombus twist, the closed rhombus twist. You would have some weird alternative way to fold things flat that could work out, but in general, you would not have an easy time finding a tessellation in this tiling if you were trying to have things strictly determined by the tiling itself, by the physical locations of the actual tiles. But if you take it abstractly, then you can get all kinds of different patterns. I'm just going to show a couple of my favorites that are all in this tiling. And I taught a lot of these in Advent of Tess this last year. And there's also a lot more explanation in my Tessellation Academy course. So all of these patterns use the hexagon, double rhombus, triangle tiling. Yet none of them would be possible if you were trying to take the strict definition given by Lang in creating the origami tessellation. So there's really a huge variety of different patterns that you can make with this tiling. And these are kind of just scratching the surface. So that's what I have to share today. There's a lot more to explore in these tilings, and I encourage you to check out some of my other videos as well. I mentioned the one on cursed triangle twists and cursed square twists, the one on the fundamental structure series that's talking about these tilings where you can alternate two different twists. I have a series on folding more repeats of patterns that's talking about, okay, in this tiling, we want to fold in rings around the center. I actually have a video that's specifically about folding in rings around the center, one about folding in stripes, and one about these pseudo tiling breaks. And those are all in the Fold More Repeats playlist. There's a couple different places where I've tried to explain, okay, what is a tiling before, and then there's also resources from other people. There's this 6 Simple Twists book from Ben Parker. There's Twist Tilings and Tessellations, which frankly I would recommend more for people who want to write code about origami tessellations. It's not a book that's going to help much with folding process of grid-based origami tessellations, but it is a fascinating resource on like the deep mathematics behind a lot of these things. And then there's, yeah, so many different patterns that I've published over the years. And another place to see more about tilings is in the Advent of Tess ebook from 2024. I did put in a bunch of drawings of tilings for each of those patterns. And in Tessellation Academy, so the smaller dose would be the Tessellation Academy Volume 1 ebook that you can find at gatheringfolds.com, also on Origami USA's online store and Origami Shop. And then there's the membership itself that also includes 2 tutorials per month. And there's just so many exciting things going on in Tessellation Academy. There's a lot of stuff that I'm able to explain in more detail because we're able to focus in on a particular tiling or a particular way of repeating patterns or a particular pairing of twists. Like we did a whole month on just the open hexagon, closed triangle twist patterns that I've been doing across a couple different tilings. So that is available at training.gatheringfolds.com/academy, or you could just go to gatheringfolds.com, click the link for courses, and that will get you to the right place. So yeah, these tilings for me really unlock a lot of ideas that I wouldn't have had otherwise. And getting away from this idea that tilings need to tie in to the physical tessellation, to the crease pattern itself, and instead saying, okay, it's an abstraction that guarantees flat foldability because of the shapes that are used and how they're connected. And then we can basically use it like a coloring book to see what different options there are for placement of symmetry points. Those uses of tilings have really unlocked a lot of new patterns for me. So yeah, Erlu, I'm glad you're enjoying Tessellation Academy. There's a lot of cool stuff coming up the rest of this year. So happy folding, everyone, and see you next week. And next week actually is a tutorial on a pattern that's a simpler version of what I'll be doing tutorials on in Tessellation Academy in a couple months. So I'm looking forward to that one. Happy folding and have a great day.